Section 3.3, we're going to take a look at three different groupings of identities. One of them are called double angles. That's the ones we're going to start with. The second one is power reducing. And the third one is half angle formulas. And what these formulas do, along with some of the ones that we did before and ones we are yet to encounter, is they allow us to find exact values of trigonometric angles. And you might say, okay, well, my calculator can do that. And the problem is your calculator actually can't do that. In many cases, your calculator does not find exact values for things. It finds approximations. And sometimes it's just not good enough. If you want to sort of have a perspective of why is that sometimes not good enough, think about things that happen with engineering when you're talking about creating like spaceships and stuff like this. The precision and the level of accuracy needs to be perfect for some things to work out. And so having exact values becomes really important in certain fields. And so this will allow us to have a better ability to get some of those exact values. Okay? So the first one we're going to look at is double angle identities. There are three double angle identities that we're looking at, cosine, sine, and tangent. And there are ones for secant, cosecant, and cotangent, but we can just flip them. So we don't need three more, okay? So we can just flip each one of these upside down, and we'll have the corresponding ones that are missing, so to speak. But you can see that the cosine of 2 theta is cosine squared theta minus sine squared theta. Sine of 2 theta is 2 sine theta cosine theta. And the tangent of 2 theta is 2 tangent theta over 1 minus tangent squared, or 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. So any of those can be used depending on the information you have. One might be preferable to the others, right? So you can use any of those on the last one. Do notice what you can't do. You can't just take the 2 that's beside the theta and move it into the front of the formula, right? We can't just move the 2 out and act like it's going to be the same. It isn't, and it isn't for any of them. Every single one of these double angle formulas does not have that as a feature. Okay, it's the tempting thing to do, right? We like to move numbers around. It's the commutative property. We do it with other things all the time, but we can't do it with trig angles. All right? So we're going to take a look at an example. Our example actually has a triangle, at least partially filled in for us and given, and it wants us to find sine of 2 alpha. Okay? So inside of a triangle, you do probably remember exactly what sine is. How do you find sine in a triangle? The sine of an angle. This angle is alpha. You bet. It's opposite over hypotenuse. Now, we don't have just sine of alpha. We have sine of 2 alpha. So let's actually write this down. Sine of 2 alpha, using the formulas on the previous slide or earlier up in your notes, on your note sheet that's separate, whichever one you're looking at. What's the sine of 2 alpha? There's a 2. And then there's a sine of, Isaiah, finish that for me? Okay, and I'm going to use alpha since this was using alphas. Yeah. So this is the formula with alphas in it instead of thetas. Okay? Now, looking at this picture, I should be able to find these two quantities, sine of alpha and cosine of alpha, but I need the third side to do that, right? We talked about solving triangles. We've been looking at this is Pythagorean identity. We've done this since about maybe the 4th day of class. So we've been doing this quite a while. You've seen this in a geometry course back in the day. So how do we find the third side? Yeah, the Pythagorean theorem. So let me just call this side C, and we will have a squared, which is 24 squared, plus b squared, which is 7 squared, equals c squared.
Is that 480?
It's 24. It's not 480. No. And I don't even have the total. I have the sum of. It's 625. So if you square these and then you add them together, it's 625. And if we take the square root, our c value is 25. So this c is 25. And I mentioned it before, but I'll mention it again. Of course, not all triangles have whole number components on everything. And those that do are called Pythagorean triples. This is a Pythagorean triple. At some point, you may actually start to memorize a few of them. So this is one that I do have memorized because I see it frequently when I'm working in trig. It's not something I'm going to have memorized, like a year from now. I get that. But when I'm working in trig, this one comes up frequently. There's a couple others that come up frequently. There's one that's a 3, 4, 5 triangle. I can't remember if we have one in our lesson today. I think we do. and it comes up. And then there's another one that's a 5, 12, 13 triangle that comes up frequently. You can find them with the Pythagorean theorem every time, but of course, those are special cases, right? Not all things, not all triangles have these whole number of values. However, having that third side now, and here's my angle alpha that we're looking at, we should be able to use this formula and find the sine of 2 alpha. So in this triangle, what is the sine of alpha? We said it's supposed to be found opposite of hypotenuse, so what is it? 7 over 25. So this one right here, the 2 stays in the front, but this one right here is 7 over 25. That's not a good 7. Let's try again. 7 over 25. And I didn't write it down, so let me go back up and do that. Again, from a triangle's perspective, what is the cosine of alpha? Adjacent over hypotenuse. And that's the other piece I need in this formula. So using this triangle, what is the adjacent over the hypotenuse? 24 over 25. All right, so this 2 is the same as 2 over 1, right? So we're going to multiply across the top. 2 times 7 times 24. What will that give me? A big number. 336 is it. Thank you, Becca. 336. 25 times 25. That's actually on my screen already. That's 625. And these won't reduce. You can try if you would like, but I can tell you they won't reduce because if you take a look back at what we multiplied to get there, there was no reducing that we could have done in that step. Right? So if there's no reducing in the step before we actually do the multiplication, there's not going to be any reducing in this step at the end either. So this is our exact quantity of the 330 or of a sine of 2 alpha. Notice we never found alpha, right? It's not necessary. We don't need to know what alpha is. We don't need to know what 2 alpha is. It's not what we're asked to find. We're asked to find the sine of that value. Okay, you ready to try another one? Another one with double angles. Okay. So this one gives us a cosine value. Cosine of theta is 4 over 5, and it tells us which quadrant we're in. So the fact that it's telling us which quadrant we're in sort of begs us to draw the picture in that quadrant. Does that make sense? So we're going to start by actually drawing this in quadrant 4. So quadrant 4 is down here, right? And if I'm drawing my angle theta in quadrant 4, it's going to look something like this. Okay, is everybody good with that? Make that a smaller font. Okay, it's going to create a triangle. Like, that's the whole point. We're going to make a triangle out of this. Okay, so let me extend this just a little bit so I have more to draw from. The triangle, again, always goes back to the positive x-axis. All this is stuff we've done before. So we're operating in the same constructs as we had before. And for this triangle, with this theta, I know that the cosine is equal to 4 over 5. So we just wrote it earlier that the cosine of an angle is adjacent over hypotenuse. So using this triangle, where is the adjacent piece, the number 4, going to go? It's on top, right? The top part is adjacent to our angle. Okay, so this one right here is my 4. That's adjacent. And then the hypotenuse is going to be the 5. The hypotenuse is always the side opposite the 90-degree angle, so this one right here is 5. Okay, so this is the one that I was alluding to just a moment ago. This is a very nice form. It is a Pythagorean triple. It's a 3, 4, 5 triangle. That third side is going to be 3. If you wanted to figure it out, if you weren't sure, if you were looking at it, then you're like, I can't remember if this is that one that she was talking about. That's fine. You can figure that out. You can call this side A or B, whichever you wish. And then you can go with 4 squared plus b squared equals 5 squared. This is 16 and 25. If we subtract, we get 9. And if you square root, we have to be a little careful. Normally, we say that this is a 3, but really it's a positive or negative 3, and I do have a direction because of the quadrant I'm in. What is that b value in this quadrant?
Negative.
It's actually negative. So whether you're thinking about it from doing this formula perspective, or whether you're thinking about it from having drawn the picture and recognizing it's a Pythagorean triple, but then you know which quadrant you're in, either way, it's going to be a negative in this one. So this value right here is going to be -3. Okay, everybody all right with that? Okay, this question asks us to find all three of the double angles that we have: sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. And you have more than one way to do each of those. Well, not all of them, but especially when we get to tangent, you will. We've already done a sine one, and so that should be sort of on the forefront of your memory, is that this is 2 sine theta cosine theta. That's the formula for the double angle there. The 2 is as written, and the cosine theta was given to us. We know that that's 4/5. The sine theta is the only thing I need to get out of the triangle. So using this triangle, what is the sine of theta? -3/5. So everybody see where that came from? Okay. Now again, if you take a look for a moment here to see if there's any simplification, that's a good place to do it because it's all in nice factored form, right? There's not. And I can rewrite this 2, if you would like, as 2/1 to help you see it. You're looking from top to bottom of fractions and you're looking along diagonals. There's no simplifying that can be done. These denominators are both 5s, and there's nothing that's a multiple of 5 in a numerator. So the only thing I can do is to multiply across the top. So I have 2 times -3 times 4. It's -24. And in the bottom, it's 25. Okay. Cosine of 2 theta then. Okay, well that had a different formula, right? So let's go back here just a second and grab it. This one's actually squaring pieces. So it's the cosine squared minus the sine squared. So when I write this one down, that's the first thing I'm going to do. I'm going to write that this is the cosine squared of theta minus the sine squared of theta. That's the formula's definition. But what that means is I'm going to find the cosine value and square it, and I'm going to find a sine value and square it. And I know both of those values because I just used them, right? So what is the cosine squared? What is the cosine value? I should say it that way first. It was 4/5, right? Cosine of theta is 4/5. What is sine theta? -3/5. So we're going to square 4/5. What's that going to give me? 16/25. There's a subtraction sign in the middle. And then I'm going to square this next one. It is negative, but what happens when I square a negative? It becomes positive. So I'm going to get a positive number. The negative in the middle is just coming from the formula, okay? So I'm not getting a negative number here when I square this. That negative is a part of the formula. So what is -3/5 squared? 9/25. And, 25. And then what do we get when we subtract 16/25 minus 9/25? It'd be 7/25. Now, there's a third one. It's not on this slide because I don't have space for it. So I'm going to switch slides. But when I switch slides, I want to take this picture with me. So I'm going to do this. Okay. Tangent of 2 theta. Now, we have lots of options for tangent of 2 theta. So I want you to take a look back, and I'll let you guys pick. We have equation 1, equation 2, or equation 3. Which one do you want to use? They're underneath it. So the easiest one. They're all going to be about the same. You just need to pick one. 2. Okay, so Braden says 2. Are we good with number 2? Yeah. All right, so that means we're going to use this formula. Is everybody good with that? Okay, if you want to be really adventurous, use a different one, and we'll compare notes when we get done. Okay? Your call. All right, so we're going to use 2 cosine squared minus 1. So this is 2 cosine squared of theta minus 1. Okay, so the 2 is part of it, right? We know what the cosine value is. What's the cosine value? 4/5, thank you. It was given to us, right? It's being squared, and then we're going to subtract the number 1. All right, so let's square 4/5. We've done that before. What's 4/5 squared? Yep, 16/25, and this 2 at the front is like 2/1. So what happens when I have 2 over 1 times 16 over 25. 32 over 25. I'm going to subtract a 1. So subtracting 1, common denominator is 25 over 25. So what is 32 over 25 minus 25 over 25? Oh, hang on. Something happened. That's not right. Nope. What is going on? I think the formulas are written down right. I don't think there's a problem with that. I have the tangent. I have the first one is the one that I'm using. Oh, and I see why it's not lining up on your paper now that I'm looking at the top of my paper. I didn't get those lined up right.
Another formula.
Okay, let's scrap this for a moment. I'll go back and figure out what I have written down wrong. Let me use the one that I've got on my paper. I don't know. I'm not sure what's going on. That's okay. We'll come back to it next time. Let's use this one. I know this one's right, and I'm going to show it to you with another way of doing this. But let me do this one first. Okay. In my picture, what is the tangent of theta? Close.
It's -3.
Yeah, -3 over 4 is tangent of theta. And then we have 1 minus, and then I've got the same thing, -3 over 4 in the denominator squared. All right, this is actually the first case today where we've had something that will simplify. This 2 will simplify with this 4, right? Right, so I can just put a 2 here. So this numerator is actually the same thing as having -3 over 2. My denominator is 1 minus, and we did this before as well, 9 over 16. Oops, there we go. All right. Okay, we tried to do this a minute ago, and I was messing up with something in my formula. But this is 16 over 16. So I have -3 over 2 over. So what is 16 minus 9? That would be 7. So this is 7 over 16. And do you remember what we do when we try to divide fractions? Yep. Keep, change, flip. I'll multiply by the reciprocal. I'm going to take the denominator. I'm going to flip it upside down and multiply. There is a simplification here as well. So this 2 and this 16 will simplify to an 8. So I end up getting -24 over 7. That is the right value, -24 over 7. And I want to show you that it's the right value without using formulas to do that. So let me show you something just a second. I'm going to take this out. We'll fix it later. But I want to take a look at this from the perspective of what we know about tangent. What is the relationship of tangent to sine and cosine? The one that I had you memorize. You don't get to have a sheet that says. Quotient identity, sines and cosines. Tangent of theta is sine of theta over cosine of theta. Do you guys remember that one?
Yep.
Yes, okay, I knew you do. And it's true if we have the double angles as well. So if I want the tangent of 2 theta, that's the same as the sine of 2 theta over the cosine. Cosine of 2 theta. Okay, so it works for any angle, so it'll work for the 2 theta angles as well. So why do I mention it? Well, I mention it because we already went through the trouble of finding the sine and the cosine over here, right? We know that this is sine, and we know that this is cosine. Agreed? So I could also use these and divide these directly without using any of the formulas for tangent of 2 theta anyway. So right now, let's see, my sine is -24 over 25. And my cosine is 7 over 25. Y'all good with that? And what would I have to do? This is the same thing we did before. We'd have to flip them, right? So if I rewrite this by dividing the denominator, or taking the denominator, and changing it, flipping it, it'd be 25 over 7. And what happens to my 25s? They're going to cancel out. So it's going to leave me with the -24 over 7. I mention this because this is pretty straightforward. I like this way, but it hinges on the fact that we already found sine and cosine. If we were asked in a problem just to find tangent of 2 theta, it's probably not worth our time to find the sine of 2 theta and the cosine of 2 theta to divide them. It's probably worth it to actually use one of the other formulas instead. Okay? So we will come back to whatever's wrong with my formula next time, but let's keep moving for the moment. Is that okay on that one? Okay, we've got the tangent of 2 theta. Okay, have one more example for double angles before we move on to a different set of formulas. This one wants us to write the expression as the sine, cosine, or tangent of the double angle. So this one's tangent. This is how the directions will look for all of these like this. And this problem, the way it's written, matches one of the double angle formulas on the right side. So over here, there, it actually matches this, right? That's what it looks like. It looks like 2, and then it's got tangent of something, and 1 minus the tangent of something. So that's actually exactly the formula that I can change into the tangent of 2 times the angle. But what's the angle in this particular problem? Yeah, this angle is pi over 12. So in place of the theta, I'm going to write pi over 12, like this. That's very friendly. And the reason it's friendly is because when I clean up this angle inside, it's going to be an angle I'm familiar with. Right? Pi over 12 is not an angle I'm familiar with. Right? It's not one of the unit circle ones that we worked on. It doesn't match anything that we've memorized. It's not a friendly angle. But pi over 6 is great. So when I simplify this 2 and this 12 will cancel, and I have the tangent of pi over 6, I can do this directly from my unit circle. So now I'm back at the unit circle, right? So here's my unit circle, and I'm down here at pi over 6. Oh, that's not good. Let's try that again. Pi over 6. How can I find the tangent value right here? What is it? It's y over x. Right. Okay, so this is, I'm going to jot it down the way that you mentioned it, Melody. It's y over x. What is this ordered pair? Do y'all remember?
1/2, or it's root 3 over 2 1/2.
Root 3 over 2 1/2. So the y value is 1/2. And the x value is square root 3 over 2. You could also think of it as sine over cosine. Something wrong? Oh, yes. So we're going to simplify this. We're going to multiply 1/2 times the reciprocal. Apparently reciprocal is our theme of the day. And our 2's will cancel. And we're going to get 1 over square root of 3, which we're not going to leave like that. What are we going to do? We're going to rationalize it. How do we rationalize? Well, for the most part, the ones we've been working with thus far, is we just multiply by that value. So this ends up giving me square root 3 over 3. All good? Okay, we're about to do a different set of formulas. You ready? Okay, the next set of formulas are called our power reducing formulas. I think those showed up okay on your notes, but they're not stacked up funny. Okay, power reducing formulas. Our sine squared formula is the same as having 1 minus the cosine of 2 theta over 2. Cosine squared is 1 plus the cosine of 2 theta over 2. And tangent squared is 1 minus cosine 2 theta over 1 plus cosine 2 theta. And I hope that as you're looking at tangent squared, you're like, well, that kind of makes sense because those are components, each the numerator and the denominator, of the sine and the cosine from the previous 2 steps. That's exactly what's happening. So what we're able to do is we're able to take something that's a squared angle and simplify it. And just to give you a reason for doing so, because you might be like, well, it was easy enough, and in the problems that we did, it was easy enough to find the sine angle and then just square it, right? The sine of it was like, 3 over 4. We squared, it's 9 over 16. What's the deal? So when we do work with, as I was mentioning earlier, that he's ready to do some calculus. When you do get to calculus, if your degree plan requires you to go to doing that, Calc 2 is actually where this power reducing formula comes in really, really handy. And we aren't able to actually complete the things we need to without it. There's not another method. This is the method. So that's where this sort of gears toward, but that's how all the math is, right? You learn something somewhere so you can use it somewhere else. You may not get to the somewhere else, but some of you will. And so this is where it actually encounters it with trig, and it's utilized in Calc 2. So let's actually take a look at how we use these, though. So this particular one, I chose something that's a little bit more complicated because I wanted you to see how it's used in a more comprehensive way. So it says we're going to use the power-reducing formulas to rewrite the expression without powers. It says no power bigger than 1. We're not going to have any squares or powers or anything. We won't have any powers when we're done. All right, so here's the way that this works. First of all, you can't just say, oh, look, this one says cosine of 4x. So I'm just going to do all of this, and I'm going to replace the 2 with the 4. Right? I mean, that's not how this works. That's not how powers work. And to give you some reason why, you can think about what happens when we square things that are in binomial form. So some of you on different tests have made the error of doing something where you've had addition, like a plus b squared, and you've accidentally written down that this is a squared plus b squared. And we've talked in class about the fact that that doesn't work. So you can't square individual components. You can't change 2's into 4's. There's nuances when we deal with different operations that don't work, okay? So you can't just change things out. That's not the thing. But what you can do is you can rewrite this. So we're going to rewrite this. This is going to be written, the 10 at the front's fine. We're going to leave the 10. But we're going to rewrite this as the cosine of squared. That's what a power 4 is. It means you're squaring something twice. If you don't like it that way, you're welcome to write it this way, cosine of squared and then cosine squared like this. It's the same thing. Okay, so pick your favorite on those two. Since mine's already in this form, I think I'll just leave it. What this means then is that I can actually use that formula for each of these individually. Does that make sense? Cosine squared is a formula I have. The cosine squared is actually equal to 1 plus cosine over 2. Okay, and it's cosine of the double angle, cosine of 2 theta over 2. So when I rewrite this now, 10 stays, I will rewrite this as 1 plus cosine 2 theta over 2. And then I have another 1 plus cosine of 2 theta over 2. I've just replaced both of them. Now, I'm going to find out pretty quickly that this doesn't actually end the problem, because as I multiply these back together, I'm going to end up with a power of 2 still. It's okay, but just sort of be aware of that. Just because you've made one substitution doesn't mean that's the only substitution that you may need to make. I would like to sort of regroup these over 2's. If I were to multiply these 2 over 2's, that would be over 4, right? And I'm going to move that to the front with the 10. So as I'm simplifying this, it will be helpful for me to think about this as 2 over 10. I'm sorry, 10 over 4 is what I meant to say. 10 over 4. We'll reduce it in a second. But I'm just moving the 4 denominator out with the 10 coefficient in front. Is everybody okay with that step? And then on the inside, what I'm going to do is I'm going to have to FOIL this out. So I'm going to do first, outer, inner, and last, right? So I'm going to FOIL this. So if I FOIL this, I'm going to get a 1 plus a cosine of 2 theta plus another cosine of 2 theta plus a cosine of 2 theta, and it's squared. So I'll put the square there. And lo and behold, you have a power of 2 showing up, as I mentioned we would, right? So we're not going to be done even after we sort of combine the pieces here together, because I still have a power, and my directions said no powers when I was done. All right. I can combine these, though, so that's nice. I'm going to reduce my 10 over 4 at the front to being a 5 over 2. And I'm going to combine the like pieces. This is 2 cosine 2 theta plus the cosine squared of 2 theta. Now that's as cleaned up as it's going to get. I can distribute the 5 halves in. That would be okay too. That would be another version of this. But the truth is I'm not finished, and the reason I'm not finished is because I have a power. So I have to use that power reducing formula for this one now. All right? All the other pieces aren't going to get manipulated. They're fine. They are just fine. So when we do this, we're going to rewrite them. So this is 5/2. I have 1 plus 2 cosine of 2 theta. But I need to use the power formula, the power reducing formula for cosine squared. Well, the power reducing formula for cosine squared, it's on this screen already, is that I'm going to do 1 plus cosine of a double angle over 2. So this will be 1 plus the cosine, but it needs to be the double of this angle, right? This is my current angle, 2 theta. And if I double it, I'm going to get a 4 theta. So this is actually going to be a 4 theta now over 2. Okay, every time I utilize that formula, I double the angle when I do the other side of it. So I'm doubling my 2 theta to be 4 theta. All right, so this is kind of messy looking. We are going to simplify this, clean this up a little bit. I think I need a little bit more space, so I'm going to shift this over. We'll move it up here. So the 5/2 is going to stay the same in the front. And I'm going to get a common denominator. So I want to write each one of these over 2 so it can combine with this one that's over 2. Is that all right? Okay, so we're going to have a 2 over 2. We're going to have plus, now it's going to be 4 cosine of 2 theta over 2. And we have a 1 plus the cosine of 4 theta over 2. Those are my pieces. They're all over 2 now. We can merge the fractions together. I'll write it out. Feel free to not write this step. I don't know that I necessarily need to, but I'm going to do it just in case somebody needs to see it. We're going to put all the numerators together. And a couple of the numerators will simplify, right? Here's a 2 and here's a 1. Those will become 3. I'm also going to move at the moment this 2 outside with the 5. So this will be 5 over 4 now. And I'm going to have 3 plus 4 cosine 2 theta plus the cosine of 4 theta. We have one more step. Is this step okay? Does everybody see where all the pieces came from? Jonas, are you okay? Your expression looks a little concerned. No, we're all right. Okay. We are going to distribute the 5/4 through. So this 5/4 is going to get multiplied by each one of these coefficients. So 5/4 times 3 would be 15 over 4. Remember, you're just multiplying the numerator by 5, or by 3, excuse me. When I have 5/4 times 4, the 4's cancel. That leaves me with 5 cosine of 2 theta. And then on the last one, it doesn't have a coefficient, so it's just 5/4 cosine of 4 theta. That is not a very pretty expression. Agreed? But it is as good as it's going to get. It's not going to get any better. Okay, any questions on that? All right. Brielle, yes. Do you mean from here to here? Like this step? And then going up to there? All I'm doing is getting common denominators on that step. So you're asking me to talk about this step right here that goes up. Yeah. So I'm rewriting the number 1. This right here is the number 1. It's just written as 2 over 2. This right here would be the same thing with a 2 multiplied on top and multiplied on bottom. Okay, so my 2 on the top became a 4. And then this one stayed the same. This one's equal to what it was before. And then because they all have common denominators, we can now combine the numerators together. So all 3 of these can actually be written over the same denominator. Is that good? Okay. All right, we have one more set of identities in this section, so let's take a look at them. These are the half angle identities. And man, I'll tell you what, if you thought the first ones were messy, these ones look really bad. We've got some square roots involved. We've even got pluses or minuses in front of them involved. Man, oh man, half angle identities. These actually come about from taking your double angle identities and solving them the other direction. I mean, that's where they're coming from. But these are our 3. And once again, tangent has a couple of options, 3 options. Tangent also has a 4th option, which is just to divide the sine and the cosine if we'd already found them, right? So we kind of have 4 options for tangent when we're working with these. But these are the ones we're going to be working with. And we're going to take a look at these as it relates to a couple of examples. We at least have time for one. We'll see about the second one. This one says to use a half-angle formula to find the exact value of the expression. Now, 112.5 degrees guaranteed is not on your unit circle, right? At least it's not one of the memorized ones because it's got a decimal. None of the angles in the formula that are in the unit circle we memorized had decimal forms, correct? So we need to get that 112.5 into something that's friendlier to work with. So taking a look at these tangent values, which one would you like to take a look at changing it into?
Which one did you do on the notes?
Do you want me to do the one I did on my notes? We can do that.
Last time you did.
The one that we did on my notes is I did this one at the end. Do you want to do that one? Okay. So we have 1 minus the cosine of alpha sine of alpha. Notice the change in here. This is alpha over 2, and these are alphas, right? They're double the other one. So whatever this one is, how are we going to find the second ones? We're going to double them. Is that okay with everyone? We're going to double them. So taking a look at this over here, I need to know what this is if I double it, right? So what is 112.5 if I double it? What is it? It is 225. Okay, is that okay with everyone? Okay, that's the angle that's going to be in my formula. So I'm going to have the cosine of, 1 minus it. 1 minus the cosine of 225 divided by the sine of 225. Yeah, 225 is on the unit circle somewhere. You're right. So does anybody know 225 where it is on the unit circle? It's in quadrant 3. Which of the quadrant 3 ones is it? Is it the one that's closer to X, closer to Y, or halfway? Yeah, it's halfway. It's down here. It's the 45 one that's down here. So this is 225. Okay, everybody good? All right, so at this point right here, what are my sine and cosine values?
2 over 2. They're negative.
They're square root 2 over 2's, and then let's make sure we have our signs right. What are our signs?
Negative.
They are both negative because I'm in quadrant 3. So this is the ordered pair I'm looking at. This is why it was so important for us to get that unit circle down about a month ago, right? Is that it keeps coming back up. We keep having to use it, okay? So the sine value and the cosine value are actually the same thing here. So this is 1 minus the square root 2 over 2 divided by the square root of 2 over 2. Okay, is everybody okay with that? Oh, I need my negatives involved. Sorry, I left them off. Let's put them in there. How about that? Is that better?
Can you just change it to 1 plus?
We can, yeah. So on the top, I have minus a negative. That's addition, right? But it kind of got a mess, admittedly, right? I got fractions inside of fractions. And not only that, but the numerator also has addition and subtraction in it, which is also unfriendly. So there's a couple different ways we could handle this at this point. Somebody suggest something for me. Oh my goodness, we talked.
You know that the top one is going to simplify or like add to just root 2, right?
The top is not going to add to just root 2. Nope.
You fix the bottom and then keep change flips.
You could. Oh, Jonas just wants to pray. Is that what you said? We should just pray. We should just stop and pray. Brielle's nodding. I've got some Bethany's nodding. Yep, looks pretty good. Okay, how about this? Would you like to get rid of the fact that there's like multiple fractions involved to start with? Okay, so let me show you this. This is actually a really cool trick. It's not really a trick, but it's something that we don't often think about this way. There's a little denominator in the top and a little denominator in the bottom, right? What are those denominators? 2's. Let's just multiply by 2. Watch this. Let's do it. We're going to multiply by 2 on the top and bottom. Why in the world is that nice? Well, it applies to all the pieces. And what happens to those little denominator 2's? They vanish, they cancel, they multiply to 1, whatever words you'd like to use. But let me actually write this 2 over here so that I can cancel it nicely. That 2 gets multiplied over here. Okay, so on this one, The 2 cancels with the 2. That's kind of the point. And down here, the 2 cancels in the 2. And there's no more fractions inside of fractions. I still have the addition and subtraction to contend with on top, but there's no more fractions inside of fractions. So I have a 2 at the front. I have a square root of 2 for the second piece. And I have a negative square root of 2 on bottom. Okay. That's always my go-to. I like to get rid of the fractions as quick as I can. Okay? So flipping things around works just fine, but this actually gets you there faster. I eliminated my fractions. I still can't have the square root of 2 on bottom. So what do I have to do about that? We're going to multiply by square root of 2. So we're going to do that on the top and the bottom. Multiply by square root of 2. Make sure when you do that on the top, you distribute it, because that's a common mistake to forget. So I'm going to have 2 square root of 2 on top, plus, what happens when I multiply square root of 2 times square root of 2? You get 2. They don't cancel, but it cancels out the square root part, right? So the square root of 2 times the square root of 2 is just 2. So on the bottom, what is the negative square root of 2 times square root of 2? It's negative 2. Okay? There's one more thing we can do, and it's the last thing we're going to do today. We're going to simplify. What can we simplify? The 2's. Now, I can't simplify the square root 2 part, right?
No.
It's underneath a radical. It's going to stay put. Don't manipulate with it. But the coefficients on each of these, here and here and here, are all 2's, which means I can divide all of them by 2. So on the top, that will give me square root 2. On the second piece, I'm going to get that to be just a 1. On the bottom, I'm going to get it to be a negative 1, which we could have dealt with at the same time. What happens when I divide by a negative? It just changes all my signs on the top, right? So if I divide the square root of 2 by a negative, I get negative square root of 2. And if I divide the 1 by a negative, I get minus 1. So this simplifies to negative square root 2 minus 1. Grab your calculator real quick. I want to verify with you that we did it right. I haven't checked this, so it might just blow up in my face, but we're going to give it a try.
That'd be crazy.
It would be crazy. All right, I would like for you to type in your calculator negative square root 2 minus 1. It's going to give you an ugly decimal, okay? It's going to be an irrational ugly decimal. That's fine. Just find it. Did you find it? Did it work? Did you get a value? Yeah. Ugly decimal. I got a few people saying ugly decimals on my screen, right? Great. Make sure you're in degree mode. Make sure your mode says degree. And then I want you to type in where we started. Tangent 112.5 and press enter. Hold my breath for a second. It should give you an ugly decimal that Olivia says it's matching my other ugly decimal. Do the ugly decimals match? Oh, goodness gracious, I'm so glad. That's good news to end on for today. All right, we will stop there.